Good morning to all. I am Devashish Pal. I work in the spacecraft operational area of ISRO Tracking Telemetry and Command Network. Today I'll be presenting of the mission design and the operation aspect for the space science missions. Yeah. So my presentation to start with, I will just start with the mission life cycle. Typically, we see how a mission is conceived for any space mission. So this is true for any of the missions. So to start with, we have a science objective or the mission objective. For example, if it is a Chandrayaan-2 mission, the mapping of the moon is the one of the example. If it is a Aditya kind of mission, so seeing the sun and getting information from the sun is the one kind of science objective. Similarly, if you have an India remote sensing mission, so cartography or oceanography or weather monitoring can be the mission objectives. So these are all the mission objectives to start a mission. So once we have a proper mission objective, we go to the mission design. So mission design happens with the two segments. One is the space segment, where we talk about the satellite design. And along with that, parallelly, the ground segment design also start. So I'll be deliberating more on this. So once the mission design is done, we go for the subsystem realization. So where all the packages are being developed by the subsystem and delivered. Okay, so once the subsystems are there, so it goes for an integration process where all the equipments, all the panels, all the electronics and all the sensors are put together, and we are getting ready for the integrated spacecraft. Then the spacecraft move to the GCO. The GCO stands for the ground checkout, where we do all the kind of testing, the all contingency mode, all the normal mode test to end, all the operational checks being done. So after that, the test is over, we go for the pre-launch simulation, followed by the actual launch of the satellite. So in between screen, if you see, it is the spacecraft operation center, where from all the operations are being we are controlling. And then once the launch is happened, satellite get injected on the orbit. Then start followed by the launch and early orbit phase. We acronym as a LEOF phase, where after launch the satellite gets separates and it does some of the primary operations. So that called the launch and early orbit phase operation. Followed by we move to the commissioning phase. Commissioning phase, what we try to do is the calibration of all the instrument, onboard instrument and the payload instrument, so that after the end of the commissioning phase, we declare the spacecraft is operational. And then it moves to the normal phase of the operation. This is the longest period in the mission life. And so it's consists of 24/7 satellite health management and other activities. We'll discuss this point in detail. And after the normal phase is over, we generally decommission the satellite. Yeah. So to get in the proper definition sake, what is the mission planning? So it's a complex planning, and with a multidisciplinary activity which starts from the definition of the mission objective, as I told earlier, and the design of the satellite to accomplish the mission, realization of the satellite, launch and operationalization up to the mission life. So this is a definition of the satellite mission planning and operation. So per se, if it is a multidisciplinary, so multidisciplinary to elaborate on the multidisciplinary, it starts from the all basic science, maths, put together all the engineering discipline. You talk about the electrical engineering, chemical, mechanical, civil. So all these parts are very, very important in the multidisciplinary when we talk about the mission operation. And when we do a mission planning, so through mission planning, we try to translate the requirement, the science requirement or the mission requirement to the operational activities, so that it can follow over the entire span of the satellite life. And then the planning the spacecraft requires the knowledge of the spacecraft. When we do a mission planning, so a spacecraft operation team should know of all the satellite elements, how they operate, spacecraft elements plus the ground segment, all the elements. They should have a very proper knowledge of all the equipments, how the space segment is working, how the ground segment is working. So this knowledge they should have to carry out the operation. And I will be talking about this space segment and ground segment in detail. Just to see what are the major goals or the major requirements, which is the mission planning is involved. First is the launch vehicle. What type of launch vehicle? It is a PSLV, GSLV, PSLV also has a different variant. JSLV also a different variant, which launch vehicle to use. So to finalize that. Okay. Then coming to the space segment, which kind of payload you are going to do. The mainframe. Mainframe starts with the structure, power. AOC stands for Attitude and Orbit Control System. RCS stands for Reaction Control System. So all this mainframe element, TTC, thermal sensors. So all this, mission team need to finalize all these equipments, how to make the satellite mainframe. And parallelly, payload team will be working on the payload design. So this is the space segment, followed by the parallel activity ground segment. That also how the ground station network should be, how many types of antenna, what all the network support is required. So those things also parallel work will be going on. Then followed by the orbit definition. So for a particular satellite, what kind of orbit it should go. I'll talk about what all the possible orbits are there. Then what kind of attitude? Attitude means orientation. What orientation satellite should be to carry out the mission goals, and followed by the mission life. So these are all the major components or elements which is very need to form up when we are designing a mission. Yeah. Now coming to the type of orbit, see we have orbit can be classified in majorly three aspects. One is the altitude of the orbit, then is the inclination, then is the shape. So to start with the altitude, we call low Earth orbit or the LEO satellites when its altitude is around 200 to 1000 kilometer. Similarly, if the altitude is 1000 to 36,000 kilometer, we call it the medium Earth orbit. And that altitude is exactly at 36,000 kilometer, it's a geosynchronous orbit. So geosynchronous orbits are wherever from a geolocation we'll see the satellite as a stationary. So that's called the geosynchronous orbit. Then it can be categorized based on the inclination also. If inclination is close to 0, so we call it as equatorial orbit. If inclination is around 90, we call it as a polar orbit. And 0 to 90 degree inclination, we have called inclined orbit. So based on the application, these orbits will be chosen based on the science application. Similarly, the type of orbit based on shape also. If we make eccentricity, E stands for eccentricity. If eccentricity is very close to 0, it's a circular orbit. If eccentricity is more than 0, we call it as the elliptic orbit. And if eccentricity is more than 1, so we call it a hyperbolic orbit. This hyperbolic orbit generally used for the escape. When we have designed our Mars orbiter mission, it gone through a hyperbolic orbit. So it can escape the Earth and go and get captured to the Mars. So this kind of deep space mission generally we prefer required for the hyperbolic orbit design. Another, just to give a few example of the how this orbit, if you go through the GPS orbit, the very popular GPS orbit, the GPS constellation, which is around 20,000 kilometer. It's having 6 orbital planes, inclined 6 orbital planes are there, and there are total 24 satellites, so which calls the geo constellation. Similarly, we have another application called orbit, which is called polar sun synchronous orbit. So this polar sun synchronous means its orbit motion is synchronous with the sun motion. So this if you place a satellite with the orbit of closely 90 degree, slightly more than 90 degree, so say around 97 or 19 degrees per second based on the altitude. So it makes a sun synchronous orbit. So its motion is synchronous with the sun motion. And these orbits are very popular for the Earth imaging satellite. Okay, now to take you through the other orbits, which is for example, if you want to go to the orbit to the moon. So this particular example is for the Chandrayaan-2 orbit. So when satellite was being injected through a launch vehicle, it was placed in 170 kilometer perigee and 45,475 kilometer apogee. So the perigee, the definition is it is the closest point from the Earth, and the apogee is the farthest point of the Earth. So that's the apogee and perigee. So now, slowly we do one by one orbit maneuver. Sequential orbit maneuvers will be planned. No? So after the end of the maneuver, the satellite will be very close to moon. So that's the intention. So this is called for the mission planning. Here the planning part important. At what time we should fire, at what place to be fired. When the moon also is rotating about the Earth. So when my apogee is close to moon also should be there. So here also timing is very important. Both of them should be coincide together. So this is what the mission planning does. So to capture the moon closely. Now, when we are very close to moon, then we have to do another type of maneuver. So we call it say LOI, or the lunar orbit insertion. If we don't do that maneuver, what will happen? The satellite will be very close to moon, and then it will escape from the moon. It will be just a flyby trajectory. So we need to have a maneuver done there, so that it will be captured by the moon and the orbit will be moon. So the first orbit, if you see about moon, so previously it was orbit around Earth. Now we have an orbit around moon. So this periloon, after the LOI, the lunar orbit insertion, the orbit was 117 kilometer periloon and Apollon was 18,000 kilometer. Now slowly from there, we decrease the orbit. Apollon and periloon both will make such a way that we have a 100 by 100 orbit achieved. So if you see, there is a series of maneuver, 7 maneuvers are there. So through that, we primarily achieve the science orbit. So now you know the Chandrayaan 2 orbit is the science orbit is 100 by 100. From there, we do all the science experiment. So to achieve that, we have to plan, so many maneuvers so that we finally will go to that particular orbit. So this is one example of the how mission planning is done to capture the moon. Similarly, Aditya L1. This is also another project where we have a closed orbit about the L1 point. L1 point, which this mission is to monitor the sun. So here also we have a period, after launch we have a elliptic orbit around Earth. Then from there we have we started journey the cruise phase for cruise phase went on, and then when we reached close to the L1 point or the halo orbit point, we did one halo orbit insertion maneuver, and we made a closed orbit about the L1 point, so that so from there we can see the sun uninterruptedly. So these are all the type of object orbit which is a very mission specific. So any design, any mission when scientifically taken, this orbit is important. So first the primary objective is to get the orbit first. So once we get the orbit, then we will go for the satellite subsystems. Yeah. So satellite subsystem, generally, satellite we having 7 subsystems, which is termed as a power subsystem, AOCS subsystem, attitude and orbit control system. AOCS stands for attitude and orbit control system. Then payload and data handling system, and then reaction control system, RCS. TTC is the tracking, telemetry, and command. Then we have a thermal system, which consists of a heater, MLI blankets, heat pipe. OSR stands for optical solar reflector. And then we have a different type of sensor, like IRU, inertial reference unit, the sun sensor, the earth sensor, the star sensor. So all this kind of, so there are the 7 prime subsystems. So which we need to decide once we go for a particular mission. What should be my solar array configuration? What should be my battery sizing? What kind of power electronics we have to use? Okay. Then if you talk about payload and data handling, what kind of, how much this actually the payload and data handling system, here we record the payload data. So how much payload data we have to record? How much data volume is it? Accordingly, we have to size the recorder. So that way. And so these are all, we'll discuss all this in detail. And some of the systems, like power system, solar array. So if you see 2 spacecraft, their requirements are different. Some spacecraft, this is IMS spacecraft, where we require not much power. So solar panel will be, sizing will be done accordingly, where we want maybe 1,000 watt of power. Then we have a GSAT series where you have a very, very huge power requirement. So then we have to design the solar panel such that it can generate a huge amount of power. So accordingly, based on how much power satellite is required, the solar array sizing will be done. So this is one of the design parameter which mission has to do. Then and the battery. So when there is no solar, when there is a solar panel can generate the power when there is a sunlight. But satellite sometimes it goes into the eclipse. When it goes into the eclipse, then the solar panel cannot generate the power. Then we need a power from the battery. So you need to put a satellite with the battery also. So battery design also is one important parameter. So based on the satellite bus, you need some battery. So here, typically we talk the battery capacity in terms of AH. AH stands for ampere hour. So maybe we have a 10 ampere hour. Then maybe we can have a wherever more battery power is required. So battery capacity is required. It can be 180 kind of AH. So that kind of based on the application of the satellite, based on the power requirement, we choose the battery. So these are all the design parameters which need to be designed during the design phase. So the another subsystem, which is called the AOCS sensors or actuator, I will try to put these three systems together because they operate very close with each other. So here the objective is the control the spacecraft attitude. The attitude means the orientation of the spacecraft. For example, if we think of like my camera axis is looks towards Earth, so always it looks towards Earth. Or if it is a Earth viewing mission, if it is a Sun viewing mission, my camera axis has to look towards the Sun. So this kinds of definition, no? This is the attitude. So this attitude need to be controlled, but we will not be able to maintain this. Why? Because of disturbance. If we do not have a feedback control loop, because of the disturbance dot, even though I put my camera axis towards Earth or towards Sun, it will deviate. So we need some active mechanism to control that, which can sense the disturbance on board and take the corrective action to reorient that. So for that, no, we have the actuators. You can see in top I have given the actuators. They are the actuators are reaction wheel. So this reaction wheel work on the conservation of the angular momentum. So it rotates. It rotates. When it rotates, the reaction wheel, if you rotate, accordingly my spacecraft also will rotate. So if any disturbance try to rotate the spacecraft, we have to rotate my reaction wheel in such a way that again the camera axis points towards the Earth. Then there are some thrusters. They have a different capacities of thrusters. So those are also the active element which requires a reaction control system. The fuel is required, either monopropellant or bipropellant. So they can also rotate the spacecraft, but it will be much faster. Reaction will rotate the spacecraft very slowly. Thrusters rotate the spacecraft very fast. So that's the difference between the reaction wheel and thrusters. Now coming to the sensors, how much we have to rotate. So that measurements we get from the start sensors. So we have a different type of sensor. We can sense the sun, we can sense the Earth, and we can sense the sun. So based on what we are sensing, we have a sun sensor or Earth sensor or star sensor. So below there are two pictures of one is the star sensor and another is the sun sensor. So now which sense either star or sun and determines its orientation. Okay, so how much axis is deviated from the Earth? So this kind of decision the sensors will be tried to measure. Now this start why so many type of sensors. See, their accuracy level is a main factor. The star sensor, they are kind of arc second accuracy. So star sensor generally, it gives 10 arc second accuracy. So 10 arc second is around the 0.002 degree. So when I control my axis, I should if I use the star sensor, I should be able to control or measure the attitude deviation of the order of 0.002 degree from the star sensor. But similarly, if you use the sun sensor, that accuracy is slightly coarse accuracy, it's 0.05 degree. But okay, so based on the different requirement, we can use either a star sensor or the sun sensor. So generally, when we design the mission, these are all things are getting finalized. Which type of star sensor to choose, which type of sun sensor to choose. So these definitions generally will be defined during the design phase of the mission. So here, just I wanted to show a case study of Chandrayaan 2 orbiter and their elements, how they are mounted. If you see the left-hand side, here all we have the payloads like a SAR payload. This is synthetic aperture radar, acronym for the SAR. Then we have a TMC payload, TMC2, IIRS, XSM payload, class payload. So one panel is completely equipped with the payload, which has to see the moon and do the image part of the moon or the mapping part of the moon. Similarly, in the top deck, if you see, they are the reaction wheels. As we shown, the reaction wheels, there are 4 in number, so they can rotate the spacecraft. Then on the top deck, we have a deployable TTC antenna also, which is required for the communication. When you want to communicate with the spacecraft, so these antennas being used. Then if you see, the down deck, we have a thrusters. So these are all thrusters. This is the black color big thruster. It is the 440 Newton thrusters, which is used for the orbit maneuvers. Then we have a small thrusters also, which is required for the orbit correction or the attitude correction both. So these are example of thruster. Now if you see this panel here, we have a star sensor. So two star sensor are adjacent. Their field of view are different, but they are adjacently mounted. Then we have another antenna, the green color part. If you see, this is called the DGA antenna, the dual gimbal antenna. This is for the payload data, the science payload data. To download this data, we have this antenna, the DGA antenna. Then we have class. This is another sun sensor, the quartz analog sun sensor. So this sensor also is mounted. Then we have another antenna here, TTC antenna. So like this, no? And if you see the panel inside also are being seen. These are all the electronic packages which is getting designed by the subsystems and delivered to the integration facility, where the integration team assemble the spacecraft, test the spacecraft, and prepare it for the launch. So here, the mission team, another prime objective of this, is the mounting. See, like where to mount my star sensor, where to mount my DGA axis, where to mount my the CAS, where to mount my reaction wheels, and which panel my TTC antenna should be mounted. So these are all the decisions, the design level we have to take, so that they are uninterrupted. Like a star sensor should not be blocked by any of the other equipments. Like DG antenna, while transmitting the data, it should not also be get blocked. Okay, so this kind of design, or the mounting, we have to study during the design phase. So once this is done, and then these packages are being delivered for the integration and test, where the satellite integration is being done. Then satellite has moved to the GCO, the ground checkout, where all the tests are happened before the launch. So as of now, we talked about the space segment, where we have seen the orbit, how it is designed. We have seen how the 7 subsystems of their use, how they have designed. So all this. Now we'll try to see the ground segment. So as I told you in the beginning, when the design phase, the ground segment and space segment parallelly getting designed together. So ground segment, these are all the ground segment element which need to be finalized after you have a proper mission definition. See, in the first prime layer, it should come the ground station network. What are the network to be used? We can have a ISRAC network alone. ISRAC network, TTC network or tracking telemetry command network, having SHAR. SHAR is the Sriharikota, Brunei, Port Blair, Bayak, Bangalore, Mauritius, Lucknow. So we have a ground stations in many places. Of course, we have a couple of more ground stations, but for Chandrayaan to have used this ground station, that is why it is only this much. Then we need to have an external ground station with the different space agencies like Alcantara, Hawaii, HBK, Cuiba. So they are external stations. We will show where they are located and all. Then we have some deep space network also, like a JPL, the Jet Propulsion Laboratory. They are a DSN network. DSN stands for the Deep Space Network of Jet Propulsion Laboratory. They have the Deep Space Network in Canberra, Madrid, and Goldstone. So we have to hire their network also for the ground for the ground station. We have to hire their telemetry and tracking station for our network. Then the other component after ground station comes the spacecraft operation segment, where we have a spacecraft operation, flight dynamics operation, schedule. Okay, and all these things we'll just try to see very closely. But to start with, we'll start with the ground TTC ground station. So TTC ground station, TTC stands for the tracking, telemetry, and command ground station. So here, the major capabilities of ground station should be, it should be acquire and follow the spacecraft along its trajectory. This particular thing is called the tracking. Then whenever I successfully track a spacecraft, I should establish a two-way communication in the spacecraft. That means we should get telemetry from the spacecraft and we should be able to command to the spacecraft. So we have to establish this two-way communication. Okay, so reception of the housekeeping data from the spacecraft for monitoring is called the telemetry. If you just remember, we have talked about the 7 subsystem. Those subsystem individual package, their health parameter, like a battery, how much current voltage it is there, solar array, how much current it is generating, along with many other parameters. Now, all of these parameters will be coming through the TTC antenna, which is the onboard. So that is called the telemetry. Similarly, for data reception, range rate, angle data, they call the tracking data. See, range rate, and angle data, tracking data, which is very much required for the orbit determination. So this is another application which will be talking a little more after some time. For that, no, we need to have range rate measurements. So this is also done by the ground station antenna, and the uplinking of the ports and reconfiguration the onboard for the spacecraft is called the telecommanding. So where we'll be sending some command to configure some of the subsystems as per our need. Like a camera is there, so we have to switch on the camera. So we have to send a particular some command to switch on the camera, so that it can image. So this is called the telecommanding. If you see, right side, we have a 11-meter antenna. So these are all the antennas which is on the ground, which communicates to the spacecraft TTC antenna for the telemetry and telecommand. And then all the network is controlled remotely. So if you see a down picture right hand side, it is a ground station network control. All the antenna networks we control remotely from our control center, network control center. Okay, this is typically a ground station. If you break one ground station, it will look like this, the component. It has a component of a downlink. It has a component for uplink. It has a component for antenna control. And then we have a computer network to communicate whatever data we are getting. It has to finally represent in a graphical manner, or it is a very manner. So that is also one part we should have. So now if you see the downlink, downlink chain configured with LNA. LNA stands for the low noise amplifier. Then we have a multi-coupler, down converters, then tracking, telemetry tracking and command processor, or TTCP processor. So the same TTCP process, this is the downlink chain. When we get the data, if you follow the red line and red curve, the satellite telemetry comes via this and goes via LNA chain, then via multi-coupler, then the down converter, then go to the TTCP, and then finally, that data goes to the workstation where we can see the data. Similarly, if I want to give some command, the command, it will go up to TTCP, and from there it will go to the up converter. Then the high power amplifier, HP is a high power amplifier, or SSP. Then from there it will go to the antenna, and the command will get radiated. So this is the two chain, uplink and downlink chain. So now uplink downlink chain only is not important. I have to move the antenna. So satellite is moving. When satellite is moving, my antenna also has to move. So for that, antenna can move in azimuth and elevation, both the direction. So this antenna control mechanism. So we have a servo system where pre-loaded angles will be there, which angle will be expecting the spacecraft. Accordingly, you have to move the antenna control unit, or ACU. So the antenna can track the satellite. So this is an antenna control system also is an important part here. This makes it multidisciplinary, where we talk about RF, where we talk about electronics, where to cover the control system. So this generally makes this a multidisciplinary area to work with. So with this, I'll come to the, we have another network of a station, and this is called Deep Space Network. Now, whenever we have a science mission like Chandrayaan, we had the Mars Orbiter mission, MOM. So they require a bigger antenna, like 32-meter antenna is there was built for the Mars Orbiter mission. 18-meter antenna is meant for the Chandrayaan mission. So we need a bigger antenna. We'll try to get why this bigger antenna is required. But this is called the Deep Space Network, IDSN, Indian Deep Space Network. This is located at Bailalu, Bangalore. So now we come why we need a very, very different size of antenna. In previous chart you would have seen, we had a 10-meter, 11-meter antenna where we can, through which we can track our IIRS class of satellite. But for Deep Space Network, why do we need a bigger antenna? So that is to do the something about the margin, because of the distance, if you see moon, it is around 4 lakh kilometers. Then so there will be, because of this path, there will be path loss. So signal will be very, very signal strength will be very low. So and to get, so that we don't have any data, we call a bit error rate. So to have a very good bit error rate, so that we don't get any error in the data, we need a bigger antenna where we have a very good link margin for the uplink and for the downlink. So I began a bit of formula. Yeah, and I have given a formula below how to compute the uplink and downlink margin. So we need always more than 10 dB kind of margin for the both the uplink and downlink, so that we have a very good amount of we don't have any error in the data. So and that is why we require a different antenna sizes of different antenna. Now, once we talked about antenna, let us look for the ground station network. So if you just recall the first slide, we have a Indian ground stations. We have a ground station which is across the world, which is being hired for a particular mission. It is not that all mission we had the ground station. It is the actually more when we call for the deep space like a Chandrayaan 2, Chandrayaan 3, Aditya mission, MOM mission. There we'll go for the external hiring the station. Otherwise, normal IIRS mission, no, we can very well manage with our Indian ground station itself. So now, if you can see, we have distributed ground station from Coiba, Alcantara, Madrid, HBK, then Mauritius, then Australia. We have Canberra. Then we have a ground station at Hawaii. I mean, we have a contracted ground station at Hawaii. Then we have a Goldstone. So this diagram shows how the ground stations are located all over the world. See, yeah. Now coming to a question, how to plan for a particular mission, how to plan the ground station network. So there are two part of that. One is the mission planning. See, we don't want to miss any major events like a maneuver. For example, there are many major events, but as I talked about earlier, the urban maneuvers. Let me concentrate to that and talk about this only. So we don't want to miss any telemetry data during the for say whenever orbit maneuvers are happening. So whatever we first will try to do all the maneuvers over the Indian station. We'll try that so that we use our own stations very much. Then if we're not able to do so, that goes to the mission planning. When mission planning should ensure that the major event happens across the Indian network station. So that is the first. But in some cases, it may not be possible. Okay, then we have to have a different station. We can go to JPL and the Jet Propulsion Laboratory of USA, and then or the ESA, European Space Stations, to hire their station so that to monitor the major events. Now it is not only to see the events. We want to keep the backup also. Second, any major events like TLI or the LOI. LOI stands for the lunar orbit insertion. That we don't want to have over a particular only single station, because if there is no backup, if due to some reason data station fail or something happens, we will not have any backup. So those kind of event, we always go for redundancy. So there only we go for we contact if Indian stations are not available of that geographical location, we'll go for the international hiring. So that is why we have many ground stations across the world. Yeah. So, okay, I think I have talked about the ground segment, the first layer, which is a ground station network, which is the following the STRAC network, external station network, JPL network, and IDSA network. Now we'll come to the second segment of the ground segment, which is another operational segment, which talk about the flight dynamics, which talk about the scheduling and the spacecraft operation. And along with that, we'll see the computer and the communication network also. Now the flight dynamics. The major objective of the flight dynamics is the orbit determination. So if you see the picture below where orbit determination is shown, see here now when the spacecraft is tracked by a ground station, if you remember, we talked about the range and range rate. That means we know the position. We have the measurement. So from there, we know we can estimate the position of the spacecraft from the range and range rate measurement. Okay, so once we know the position, then those things now will be fitting in a curve. So because the measurements generally come with a noise. Okay, so we have to remove the noise. Then we have to finally go for a particular at time t0. What is my position? But t0 talks about the epoch time. At particular t0, what is my position? or velocity. You can think at T0, we'll try to find out V0 and T0. That is my at particular T0 location, what is my position and velocity. Now from there, no, the initial condition I am trying to define from the measurements. So that is called the orbit determination. So to tell you once more, it is the ground station which measures the data. The measured data, from the measured data, we'll try to see what is my position and the velocity at time t0 from many data. See, we can have a measurements for maybe 1 hour or 2 hour continuous measurement. So from there, we'll try to find out at one place what is my position and velocity, so that we can define. It is like initial value condition. We are trying to find out the initial condition. So that is the major part of the flight dynamics, right? What we talk about the orbit determination. Then once I know the orbit determination, we need to propagate the orbit, because this is just a differential equation. If you know the initial value at a t0, if you know the p0 and v0, so you can propagate that orbit. So at every ti instant, we should be able to tell what is my position and what is my velocity. So that is called the orbit position, orbit propagation. So once we know the orbit propagation along with time, we can generate the station visibility. Like now, you have seen, we have many stations. So the satellite at which station satellite will be visible at what time. So that is called visibility generation. So this also, as a product, our flight dynamics team will be generating the station visibility. Then along with that, some of the orbital events, when is the eclipse entry, when is the eclipse exit, when the satellite on the North Pole, when satellite is on the South Pole, satellite equatorial crossing time. So these are all very much required when you do some planning activity. So these informations also will get from the orbit propagation models. Now then another major point is the orbit maneuvers. Orbit maneuvers we call is in-plane correction and out-of-plane correction. When you want to increase the orbit, we call it as the in-plane. That means the altitude of the orbit is getting increased. If we want to change the eccentricity, the plane, that is called the out-of-plane correction. So both kind of orbit correction is being done in our satellite. Okay, you can see below some examples are there to show the orbit maneuver, where first two are the in-plane maneuvers and the third one is the out-of-plane or inclination correction. Then we have to do some maneuver for the collision avoidance maneuver also. Now, as you ever know, there are many debris are there in the space. So what happens? It should not be a threat to our satellite. If our satellite, operational satellite, is very close to any debris, we have to maneuver our spacecraft, so that it should not disturb our spacecraft. So this kind of, for all the spacecraft, this status is getting generated, and we do the period. We do the collision avoidance maneuver if it is any debris, is coming very close to our spacecraft. So that is another important part, what the flight dynamics is being done. Now we quickly see the flight dynamics interfaces. So if you see the middle, we have a preliminary orbit determination. This is another thing which orbit flight dynamics does, called the preliminary orbit determination. This is after launch, when satellite is being separated from the launch vehicle, with a very minimum data, with around 10-minute data, we have to get an approximate orbit. That is why it is called preliminary orbit. So with a very small amount of data, we should be able to tell what is my satellite orbit. So that is called the POD. Generally, when we are talked about tracking the spacecraft in Chandrayaan, we have hours together data. We have a full 6 hours data, 7 hours data to do the OD, orbit determination. But preliminary orbit determination is different. Then we have a very limited data. From there, we have to get the orbit and give this information to all the ground station, so that they can properly track the satellite. So that's the challenge here, which flight dynamics is doing. So generate the POD, and very quickly they have to generate the tracking angles. If you remember, we talked about azimuth and elevation angle for the ground station. So this from the orbit, from the satellite position, we have to get what should be the antenna azimuth, and very fast. We have to give across all the ground station. We have to give that information, so that they can easily track our satellite. Then of course, if you see the spacecraft operation team also, they are delivering the maneuver plans. Like no, there is orbit, if there is an orbit decay or orbit increase, no, those called maneuver plans. So those thing also done by the flight dynamics. Then we, as you seen earlier also, the space situational awareness, the DSSM. This is the DSSAM or the SOPA. So this is the situational awareness where where proximity reports are getting generated. This is the place where we track the debris and see any threats are there from the debris or not. So that information. So we give our state vectors, the orbit solution, to this space situation awareness team, and they see whether our spacecraft is coming very close to any debris or not. If they are coming very close, probability is high, collision probability, then we maneuver our spacecraft. Okay, so this is what another important aspect. Then of course, different other divisions like scheduling, the payload users are also, and many external. Many external customers we have from whom to whom we are giving our POD results and the orbit product solutions. Okay, this is to tell the perturbation forces of the satellite. So this is the main forces which will put our satellite, the orbit decay will happen. Okay, so one is the lunisolar attraction. If you see the solar gravity or the gravitational field of the Earth, aerodynamic drag, solar radiation pressure. So they are the major sources of the perturbation, which will not keep your satellite in a particular place. It will move. It will try to move the satellite. Sorry, not move. It will try to decay the orbit. So then now periodically you have to do orbit maneuver to put it back in our mission orbit or the science orbit. So these are all the perturbations what is happening. Now just to do a case study, I have taken one case study for Chandrayaan to orbit, how the Prelude and Apollon. See, if you know, we have a science orbit for Chandrayaan is 100 by 100 kilometer. Now, once it will not be always 100 by 100 kilometer. If you see, this point, wherever I have written the OM2, here it is 100 by 100 kilometer. But as the day goes, this perigee altitude keep decreasing. It comes to 70, and the apogee altitude goes increase. So it is 100 by 100 maybe for only one day, but it keeps decreasing. But if you don't do any orbit correction, what will happen? After 6 months or so, the perigee point, it will touch the moon. So that is why we have to again after periodically we have to do the orbit OM, so that again we maintain the 100 by 100 kilometer orbit. So now here if you see, we have done a pair of OMs, OM number 3 and 4. If you do OM 3 and 4, again we will maintain 100 by 100 kilometer orbit. Then from there again perigee will come down and apogee will go up. So again we have to do another OM. So like that, periodically we have to do the orbit maneuver, so that we maintain the altitude of the science orbit, that is what we call as a 100 by 100 altitude. So that is being maintained. So this is one case study I thought just I'll share with you for the better understanding of the orbit part. Then comes the another important area, which is called as a scheduling, which is called multi-satellite scheduling and the payload programming. The multi-satellite scheduling, because we have seen, we have many ground stations and we have many operational satellites. So this ground station and the satellite, we have to map each with other. So which spacecraft should track which ground station based on the operational requirements. So this mapping is done through the scheduling algorithms. So this has been optimally done, so that all mission objective is getting satisfied through this algorithm. So then it's just a map of the space segment to the ground segment. So then other than that, there are many other interfaces which schedule have with the flight dynamics. Flight dynamics give the station visibilities to the scheduling, and then they are, with the scheduling, with that they will take the satellite, number of satellite and the ground station, and they will map. But the visibility is generated by the flight dynamics. Similarly, the spacecraft operation team, they have the operation requirement. Their operation requirement need to be satisfied. So accordingly, they have to plan the satellite and the ground station. Then they also handle the pre-launch simulation. Then we have many external agencies. It's not only we have Indian. We have a network with the KSAT. We have network with SSC, that is Swedish. We have a network with ISA, Kepler, NASA, NOAA, INPE. all this external agencies are also being involved in satellite. Sometimes we take passes from their network, and they also take from our ISRO network support. So all this inter-agency handling is done with the scheduling, and this is the only the TTC schedule which they generate. Along with that, they do the payload programming also. Payload programming. So what time my payload should be there? So just going before the payload programming, for the science point of view, I want to tell there are two types of orbit: the sun-synchronous orbit and non-sun-synchronous orbit. The sun-synchronous orbit, where the sun and the orbital plane, they are the angle between the sun and orbital plane always same. So then with that manner, what we will get, the illumination condition on the ground where we image is all the season it is being saved. So this is the IIRS mission. Typically, all the IIRS mission, if you see, they follow the sun synchronous orbit. So payload will happen in the all the season. All payloads can happen in all season. But if you go to Chandrayaan-2, it is not so, because it is not sun synchronous. This orbit is not sun synchronous orbit. Sometimes if you see, the sun is along with orbital plane, sometimes it is 90-degree with orbital plane. Okay, so all kind of variations are there. So for Chandrayaan type of mission, we have to, when you plan for a payload, it is a seasonal payload. In some season we can do optical payload, some season you cannot do optical payload. We can go for the like a SAR payload, the synthetic aperture radar kind of payload, where the ground illumination is very less to the subsatellite points. We cannot do optical imaging. We can do the radar imaging. So this kind of planning is very, very important in case of the science mission, because mostly the orbits are non-sun synchronous orbit. So this planning of this all image is done by the scheduling team. Yeah, this is another case study just to show you how we have done the Chandrayaan-2. This is just initial phase. Right now we have covered moon with our payloads almost close to 90%. But when we started with how systematically we have planned, you can see the green part is actually the 10 minutes imaging we used to do for TMC plus IIRS. Okay, then we followed only with IIRS, which is a longer imaging, around 60 minutes type of imaging we have done. So if you can see the small strips, big strips. Okay, so like that, we periodically plan, systematically we plan the imaging. So at the end of some time, we should get a full moon coverage. So this planning has been done from 2019, from 2019. Since launch, we have doing this planning. So effect of that, now we have complete almost more than around 90% of moon is been covered through IIRS. Okay, so now moving on to another important part. This is the launch and RB orbit phase. I thought I'll just talk about it also a little more. This is the time when you see the launch. What are all the things happen on the launch day? The launch day typically, we call this a launch and early orbit phase. So here, typically spacecraft will be powered on at T0 minus 6 hours. In general, there may be slight variation, but generally T0 minus 6 hours spacecraft will be powered on, and T0 is the launch time. So from there it will be spacecraft will be powered on, and we'll be doing the initialization commanding. Okay, then followed by that, what will happen? The liftoff will happen. The pre-launch phase and the liftoff and the launch phase will be monitoring. See, launch and the liftoff is autonomous. We don't have much. We don't have any command. This is a fully autonomous event. Okay, I mean there are many safety mechanisms are inbuilt, but it is autonomous. We can only monitor that. After the liftoff and the launch, we come to the monitoring of the spacecraft injection. So the final launch vehicle, the final module, where the spacecraft is attached to, so that it will be the spacecraft will be injected, and the solar panel will be deployment in the after the injection. Then parallelly we'll be monitoring the HK, and the commanding will be done, and the ranging will be done. So by this time, why we do ranging. We do ranging because we wanted to determine the orbit and the orbit determination. So that comes from the ranging. So and monitoring of the spacecraft health parameter. Health parameter, if you remember, we have the 7 subsystems. So all the 7 subsystems need to be monitored very closely with the subsystem expert. So they tell that their subsystems are normal. Then followed by that, what will happen? The 3-axis acquisition will happen. 3-axis acquisition and the sun pointing acquisition. This is the orientation part. As we told, no, the control system will be activated, and also we use the attitude control system to control the spacecraft attitude. Then, of course, along with that, we'll be doing the POD will be generated by this time. There, some of the activities are parallel activity. The POD generation, the preliminary orbit determination, and the state vector. Now, because just after launch, POD is very important because all this ground station with a very limited tracking data and the INS data, we have to generate the orbit and give to all the ground station, so that they can further track the satellite and make it possible to so that we can have the housekeeping data, telemetry, telecom, and further. Then the dissemination of the state vector to the tracking station, and the along with that, subsystems people will be designers will be evaluating their subsystems. Okay, so this is after the LEO phase. Then we have a commissioning phase for a short for a duration of 15 to 30 days, where all the payloads are getting commissioned and all the subsystems will be getting commissioned, and satellite will be declared as operational. And we'll move to the normal phase of the mission. Normal phase of the mission is the 24/7 operation, and presently, if you see, we have a 26 satellite, including Earth orbit satellite and the space mission like a Chandrayaan, the propulsion module, Aditya. So all these category of satellite, always they will be monitored 24/7. So what we do there? We do the spacecraft. We have a spacecraft operation procedures. So if you remember my first slide, first or second slide, where we talked about we have to make a procedure so that the mission objective is being satisfied. So this is one important part. We have make the procedures. So these procedures will follow for all the time, so that the mission objective is getting satisfied. Then 24/7 spacecraft health monitoring will happen. We do the orbit determination and the product generation. We do the payload programming. Then there are onboard. We have onboard many clocks. Those calibrations will be done. Then there are these clocks are having a drift also, so that drift also need to correct. We have to do the orbit maintenance. If you remember, we talked about the satellite orbit is always because of the perturbation forces, orbit is always perturbed and the altitude may be decreasing. So we have to maintain that science orbit always. So orbit maintenance is a regular activity what we need to do. And scheduling generation and TTC also will be done. Then along with that, if any anomaly is getting detected, and that is the main reason we are operating 24/7. If there is any small anomaly, we want to take a very fast action so that it finally does not lead to mission failure. So if you see our history, and our IIRS P6 one satellite, which is completed 20 years of the mission life on orbit. So this is by this 24/7 operation and doing all the steps that made us possible, which is the mission which is only designed for 6 years can go 4 times of that 20 years kind of thing. So that's that is the part of the normal phase operation. Now, just moving back, the terminal phase of operation, when the system degrades, or we lost the redundancy, or there is no power generation, or it is got degraded. Now we have to, we don't want our satellite to be a debris and create problem for all others. So we plan for the decommissioning of the satellite. So when we lost the redundancy, or we have some degradation of the satellite, committee decides to deorbit the satellite. So we don't want to become debris. So very controlled way, we wherever possible, we do a controlled re-entry for the non-functional satellite. So that is one part which we do always. And then some of the re-entries, expected re-entries, like human specified re-entry, recovery ships, they are the expected entries. Okay, so where we have to do the entry, but for our other satellite, which is like IIRS missions, those need to be decommissioned once its operation life payload is not functional. So there further there is no point of keeping the satellite on orbit and get it become a debris. So we deorbit the satellite. Okay. So as of now, what you was in the complete life cycle of the mission. Now, the last 2 or 3 slides, I'll just show you the other associated things, which is very much to be told that when we talk about the operations. Okay, one is the computer system and the network. See the workstation. So here, the where we see the telemetry data we call as the workstations. So workstation, the display of the spacecraft health data. The data should be processed in the real time. Then we should have a sufficient disk storage capability to store the data for the entire mission life. So for example, I told IRS 20 years completed. This 20 years data is there. This data is archived. So whenever you want for sub analysis, this data is present with us. So that kind of storage we should have. High level, high availability, and the high performance should be ensured. Then we have a WAN kind of network. With the hot redundancy we have, we cannot have a single point failure. Due to one system failure, we should not lose the satellite data, or we should not be able to do telemetry telecommanding. So that should not happen. So we need to have a multiple level of redundancies, and of course we are very secure data transfer. Also, we need to ensure. Then now to talk about the communication links. Communication links are also very important. Like if you remember, now we have a networks of stations. If you just remember, try to recall the world map where we have a distributed network. See, if you just talk about Chandrayaan-3 mission, there are 25 terminals were supported for Chandrayaan-3 mission. So for all this, all data has to come to the control center, which is in ISRO Bangalore. So all data has to come. So by how the data will come? Through the communication link. So connectivity through this dedicated link, we need to have a dedicated link between the spacecraft control center to all the TTC stations. The connectivity should be the terrestrial link like optical fiber, or through the space link. We can use a satellite link also. Some of the GSATs we're using for this link purpose. Okay, then the data can generate in the real time. Data can then offline. So real time data also should flow with a minimum latency. Offline data also need to be flowed. It is not only the real time data; it's the offline data also need to be flown through this network. And the command transmission. This is another important part. The transmission of the command from SCC to the station. This also need to be ensured. So that is why the links are very important. Then not only the telemetry telecommand, we need to talk to the station, voice communication. Typically the external stations, like ESA or JPL, we have a VOCA communication with them. We have a voice communication. So that also maintained through the communication link. Okay. Now towards the end, I wanted to show you the control center facilities. What are all the things there in the control center facility? So we have a mission control room. We have a mission analysis room, the dedicated mission control room. We have a timing display. We do have the wall mount displays. We have the audio video systems. Intercoms are there. There are headsets. We do have a lecture hall. Then video conference hall, gallery, then mission documentation room. So all this, our typical control center should have all these facilities. So here I pointed few, so that just to give an idea of what a control center looks like. And if you see the right hand side, there are some pictures are there. I think you might have seen these pictures during the Chandrayaan-3 landing time. Yeah. So these are all another few pictures which was captured during the mission, which shows the mission control room, mission analysis room, dedicated mission room. So this, and I think with this I want to stop. And the final picture, it is our MOX2 complex, where the mission operation complex 2. So what you have seen is inside this building. So with this I want to thank you all for your patience here. Thank you.